we talked earlier about kinematics of manipulators, right? So we did kinematics before we did manipulators. We'll do the same thing for 3 dimensions. Okay, so let's sort of motivate this. What we did in the past was we looked at, well, we drew the axis, and then we looked at how things rotate about the axis. Let me just call that psi, so that way it'll be much better if I do it that way. So what really is going on is I've shown a 2-dimensional image, but really this is in fact a 3-dimensional rotation, and maybe this will illustrate it better. So this is the x, this is the y, and this is the line which I drew, which is at an angle psi. So this is the 3D view of the same thing. Okay, and you are looking at it this way. Since you're looking at it this way, you don't quite see the z-axis, but the z-axis is still there. Okay, so what we did was we wrote the rotation matrix as, so we wrote frames, and then this is x1. Okay, I will not show the y1 and so on, but this is what we wrote: cosine of psi minus sine of psi, sine of psi, cosine of psi, right? And really 3D rotations is just the same thing, but there is no change in the z direction. So the way we write the same matrix in 3 dimensions is we copy paste the entire matrix, but then we put zeros in the third dimension, and put a 1 in 3 comma 3. So this is 2D rotation, and this is the same matrix, okay, same rotation, but it is shown in 3 dimensions. Okay, so what we've seen actually was a 3D rotation, but we just showed it as a 2 by 2 matrix, but really it's the 3 by 3 matrix. And so we'll be dealing with 3D rotations or 3 by 3 matrices for rotations henceforth. So this is just one of the 3 rotations. We'll call this, a better way to call this is rotation about z by an angle of psi. So I'll write it as r about z, an angle of psi. Okay, just like I showed sort of 2D to 3D transformations along the z-axis, we can also write rotations about the y-axis. And the usual, we'll use the angle theta to describe rotations about the y-axis. So that will be, well, there'll be a 1 in the 2 comma 2. At 2 comma 2, there'll be a 1. There'll be zeros on those in the second row and second column. And then the remaining parts would have the same type of formula which we had for 2-dimensional rotation. So cosine theta, sine theta, minus sine theta, cosine theta. I hope this was clear on why exactly the first element was on the 2 by 2 element was 1, because we are rotating about the y-axis. Similarly, we can write rotation about the x-axis, and we'll represent that rotation by an angle phi. So again, what you can do is 1 comma 1 would be 1 because it's rotation about x. The rows, the first row and first column other than the first element would be zeros, and then we write cosine of phi minus sine of phi, sine of phi, cosine of phi. So these are the 3 rotations which describe rotation about the x, rotation about the y, and rotation about the z. Okay, so with that, let's now talk about how do we actually represent rotations in 3D space. Those are special cases of rotations about one of the 3 axes. So in general, the rotation in 3D is represented by a rotation matrix. Let's call that R. and that has elements in each of the row and column. So let's write it like this. Okay, so there are, if you count them, there are 9 elements or 9 numbers in R, as I've shown it here, right? That's what it'll look if you have a generic 3D rotation, not about X, not about Y, not about Z, but a sort of uh, a sort of different rotations about different axes, but they eventually will boil down to a 3 by 3 matrix, and that matrix, there's no reason to believe that matrix has zeros anywhere. Now, then the question is, do we really need 9 numbers to describe a rotation? And the answer is no. And that's because the rotation matrix has some special properties. And this is something which we had written down long time back. We had written down the rotation matrix is actually orthogonal. This is I is 3 by 3 identity matrix. Or in other words, this will be 1, 0, 0, 0, 1, 0, 0, 0, 0, 0, 1. So because of this particular property of a rotation matrix, these numbers r's which I wrote down are constrained in a specific way. So a consequence of this is that you'll have ri1 square equals 1. What that means, so I equals 1, 2. So this is saying that if you look at the first column 1, right, this one, and if you try to take the square and sum these elements, so r1 1 square, r2 1 square, r3 1 square, maybe I should just write it down, r1 1 square plus r2 1 square plus r3 1 square equals 1. That's always equal to 1, the sum of that. Similarly, we have ri2 square equals 1. And then same thing for ri3 square equals 1. Okay. Another consequence of this identity is that if you take the product of two consequent columns, then you should get 0. So I equals 1, 2, 3. What that means is, so the column is 1 and the second column is 2. So if you take this column and multiply these two elements together, then multiply these two elements together and these two, and then you take the sum of them, that will turn out to be 0. Okay, so that is 0. And same thing for I2, Ri3, and then finally Ri3, Ri1. So let's number them. That's 1, that's 2, that's 3, that's, I missed one. This is 1, my bad. 2, 3, 4, 5, and 6. So what we can do is we can say there are 9 numbers. It is R11, R12, R13, and so on. But there are 6 equations, or what you can, if we talked about optimization, there are 6 constraints. So the free variables are 9 minus 6, which is 3. So what I'm trying to say is that there are only 3 free variables in a rotation matrix, not 9. Okay, which means that we can describe, so this means we can describe rotations using only 3 numbers Okay. So what are those three numbers? Well, we'll actually use angles for those numbers. So we'll just use three angles to describe rotations. So it means that we can actually, instead of taking rotation about, we'll actually take rotations about specific axes and combine them to get rotation about, so rotation about three dimensions. So how do we actually do this rotations? Well, there are many ways to do it. So we talked about these Euler, these angles about x, y, z, right? Theta, phi, and psi. So what we can do is we can actually, these three numbers. So before I say that, this is some terminology. So Euler angles are typically used to describe those three angles. Okay, so those three angles could be, what we do is we rotate successively about three axes. So we could rotate about x, then rotate about y, then rotate about z. So that's those three angles. So one of them would be about x, second y, third z. And those three numbers now describe general rotation in three dimensions. Okay. This is not a unique choice. You could also do something like this, x, z, y. So this is again another way of representing the same rotation. So the rotation is the same. So when you take a rigid body and rotate it in space, it's going to have the same final configuration, but we'll use a different way to describe the rotations. So that's one way. X, Z, Y is the second way. Then you could have X, Y, X. Okay, you're allowed to do rotations about the same axis, but they cannot be subsequent. So it can't be X, X, Y, but it can be X, Y, X. Then we have X, Z, X. Okay, so these are all combinations for X. We can do Y, X, Z, Y, Z, X, Y, Z, Y, Y, X, Y. And then finally, the same thing for X. Sorry, Z. Z, X, Y, Z, Y, X, Z, Y, Z, and Z, Y, sorry, X, Z. So there are 4 plus 4 plus 4 equals 12 ways in which we can describe the rotation. So if you have a three-dimensional object in space, let's say a box, okay, and then you're trying to describe its orientation, how do you do that? Well, there are 12 ways of doing that. There are 12 ways. Think of it this way. If you want to describe, you want to call an apple in 12 languages, there are 12 ways of describing that apple in 12 different languages, but the apple is an apple. It doesn't matter which language you choose. Similarly, the orientation is the same, just that you're describing the orientation with you can describe the orientation with 12 different ways. Okay. So we got to choose one and stick to it. And that's what people do. They choose one of the methods to describe. So there are some of these have got special names. So this one is actually called Bryant angles. Okay. I don't quite know about other notations, but that one is kind of common. What we'll do in this course is actually we'll describe rotations with this combination. This is what we will use in this course. Not that others are not good, but I chose to go with ZYX 3 to 1 because that's the one normally used for aerospace applications. And in general, people use 3 to 1 or 3 to 1. 3 to 1 just indicates it's ZYX. The other one, which is very common, is this Bryant angles 1, 2, 3. And I believe ZYZ is also sometimes used. ZYZ. Okay, but it's really, you can, as you see, you don't really have to worry too much about it. Once I show you how to do it for ZYX, you can actually do it for the other conventions. Okay, what's the time? It's 10:21. Okay, so before we get into 3 to 1 Euler angles, let me show you that rotations in 3 dimensions are not commutative. Okay, what that means is if you do rotations sequence about x and then y, so say 90 degrees in x, 90 degrees in y, and you get an orientation for the object, and then you do the same thing in the opposite way, 90 degrees about y, then 90 degrees about x, then you'll see that the end configurations are different. So let me show that to you first, then we can move on. Okay, so let's just start it on a new page. So let's see how rotations. Okay, before that, maybe I should show you this, which is rotations in 2D. So rotations in 2D are commutative. Okay, so let's see what that means. So we've seen rotations in 2D along the rotation along the z-axis, right? X, y. What this means is if you do this rotation theta 1, okay, so you end with x is x1, and then you do another rotation about x1. So now this is x1, and then you did another rotation to get x2. So that is rotation by theta 1 followed by rotation by theta 2. If you reverse the order, we will have y, x, theta 2, and then we would have theta 1. So x1, x2. So if you now do this rotation, so first we do rotation about theta 1 followed by rotation about theta 2, and then you reverse it, rotation about theta 2, then rotation about theta 1. I think I'm reversing this, my bad. So when you do this, you should actually do R1, 0, no, my bad. This is right. So if you can try to do this calculation, you take r theta 1, take r theta 2, multiply them together, and do the same thing with theta 2, theta 1. You will see that you actually end up getting what is theta 1 plus theta 2. It was as if the total rotation was theta 1 plus theta 2. You'll get the same answer. Okay, what's this? Well, that's the formula which we wrote down, right? R is c theta cosine theta minus sine theta cosine theta. So that's the formula which goes in here. So that is r theta. So you can try that and you'll see that it's basically r theta 1 plus theta 2, which is saying that you can do this rotations about a single axis in sequence, and the final result is independent of the order in which you do. Or in other words, rotations in 2D are commutative. Okay, now let's see rotations in 3D. Rotations in 3D are not commutative. Okay, I'll just explain, I'll just show it to you. You can do the same thing by calculations, but I think it's more illustrative if you actually see this with an example. So let's take an object and I'm going to show it like so. So it has distinct dimensions. So there's one axis, let's call this as z. So it's thinnest along the z-axis. And then we have x and then y. So the important thing is that x cross y should be z. Okay, so we start here. Now let's do a rotation by 90 degrees about x-axis. Okay, so imagine you're turning this cuboid about the x-axis by 90 degrees in the counterclockwise direction. So when you look at it from this side, you should rotate it by 90 degrees. So it will be like this. So when I do that, what I'll get is okay, now the x-axis will be unchanged. However, the z-axis will, the new z-axis will be like this. It's still pointing out from the largest surface area, the face which has the largest surface area, and y is like this. So let's call that z prime and y prime, because now we have a new z and a new y. Okay, you can see that z prime and y prime is the same in the body frame. Okay, it's still along the bigger surface area, like you can see, but in world frame, okay, it is in a different orientation. Okay, in fact, y prime is along z now in world frame. So we did that. Now let's do rotation by 90 degrees about y-axis. So we need to turn by 90 degrees along this axis, so it will be counterclockwise. So if you do that, what we end up with is a question. Would it be rotated in the opposite direction? The rotation you made with the arrow is clockwise from that view about the x-axis. Is that true? I don't think so. So I think it's right. So, okay, so let me do it this way. Let me just proceed and put this on paper, and then I'll show it to you visually. Like I'll turn my camera on and then we can do it. And I think that's much faster and easier, but I think for your notes, this might be easier. Let me just follow along. Okay. So if you rotate it about y-axis, which is now actually the new y-axis, then you would end up with this configuration. So y will be unchanged. I'll call that z double prime because it's shifted, and x will also change now, but let's call it x. Let's call it x double prime because it's the new frame. Okay, so that's what we get if we start doing it this way. Let's try to do it the opposite way about y-axis. So now we're rotating about the y-axis, and that's going to be counterclockwise. So it'll end up this way. I guess part of the problem you might have is maybe my drawings are not that great, and so I'll actually give you some code which will do this. I'll also show it to you with the illustration. So now we'll have the y is unchanged, but z is going to be, yeah, this way, right? It's going to turn sort of this way because that's counterclockwise, and then x will be downwards. So let's call that z prime and x prime because that's rotated. And then if you do the same 90 degrees rotation about the x prime axis, you'll end up, so rotation about x prime axis in this direction, counterclockwise, you'll end up with x will be unchanged. C prime and y. Okay, so I tried my best to draw this how I think it is, but I'll show it to you in reality by an example by showing my camera. But for now, just believe me that if you do 90 degrees rotation about x and y, you get a configuration which looks like this, which is very different from the final configuration you get when you reverse the rotations. Okay, and that is just illustrating that rotations are not commutative. Okay, now I'm going to switch my camera on, and hopefully I'll illustrate to you that this actually makes sense. Here is a box, and it has distinct dimensions, so it's easy to visualize. Okay, so what we did was we said this is the z-axis, x-axis, let's say, is this way, and y-axis is towards my left, okay, such that x cross y is z. So let's rotate by 90 degrees about the x-axis, which is this way. So rotation about x-axis is like this. So you essentially put your thumb along the x-axis and rotate wherever your fingers curl. So it's 90 degrees. So it'll be this way. Okay, now again, z-axis is going to be this way. X-axis remains the same and y-axis up. Now let's rotate about y-axis by 90 degrees. So that's y-axis. And I need to curl my fingers along, well, thumb against the y-axis and curl my fingers this way. And so when I do that, I end up this way. Okay, so remember this. I started like this, I went this way, and then it became this way. So this is how the box looks right now. You can read the lettering, right? When I start this way. Now let's try to switch the order. Okay, again, z is up, x is there, y is there. Let's try to rotate about the y-axis first. So y-axis is there. Curl my fingers along the direction of rotation. So it goes this way. That's the first rotation. Now z is pointing towards you. Y is still this way because I rotated about that, so it doesn't change. And the x-axis is down. So next, let's rotate it about the x-axis by 90 degrees. So I need to curl my fingers, well, thumb in the direction of x and curl my fingers along x. So I need to turn it this way. Okay, so this is how I end up. So you can see it's in a different orientation than what it was when I did it. Actually, so it was this way as opposed to, this is how I ended up when I did the first set of rotations, and this is how it ended up when I did the second set of rotations. Hopefully that is more convincing than what I showed on paper. There's another function which is rotation about yx, and this code basically what it does, it calls this function successively. Let me just run it first and then explain to you what's going on. So here is the results of this. What it does, it generates the data for rotation about x followed by y. So the top panel, so this top panel is rotation about x 90 degrees and y 90 degrees. So you end up that configuration, okay, starting with some initial configuration. The second function, which is shown here, does the second set of rotations. So start with the same initial configuration, then do rotation about y, and then do rotation about x. And then the key thing to note is that the final configuration here is different from the final configuration there. Okay, and so hopefully the third way, and hopefully this illustrates this better, you can use this for visualization. I've not actually shown the axis, not written them down, but you can write them down and see if they make sense. This actually should also be a good introduction to drawing three-dimensional shapes in MATLAB. So we've so far seen using patch to generate two-dimensional objects, but you can actually do three-dimensional shapes. And the way I did this was, and it's a little bit more complicated than two-dimensional. You actually need to define vertices for the cuboid. Okay, so there are vertices, and Lx, Ly, Lz are basically the lengths of the cuboid, and then you need to tell it something about the faces of the cuboid. So define the vertex, define the face. Once you do that, then it's just a matter of using a patch object. Here's the patch. It's okay, there it is, patch. So what I do is, there's a single patch for the entire box. You give it the vertex. This is new vertex is because I then need to do some transformations to rotate, but it takes the vertex and does some rotations. We talked about that in a bit. And then takes the faces, puts them down. You need to do nothing with the faces, and then you need to put some color to that. Frankly, I did this once, and since then I've not really thought too much about the code. I would not recommend, I mean, you can try to understand it and so on, but I would say you just want to take my code, or for that matter, you can download some code on the internet which does this three-dimensional shape and just keep using them. But I just want to illustrate that you can do three-dimensional things with MATLAB, and it's a nice visual tool. There is some rotation matrices involved, as I've shown you, which is you multiply first x and y, or you can do the opposite, which is r, y